All right, lesson 6, derivative examples, part 2. We'll keep looking at examples involving the shortcuts from the previous video. Some of these examples get a little crazy. I put in some challenging ones, but that's a good way to know if you're really confident with all these different rules, if you can do some challenging ones too. The first section appears to be practice with products and quotients, although sometimes you have little tricks that can help make your life a little easier. You certainly could try to apply product rule here in this first one. However, I think the easier approach, just FOIL it out first. FOIL it out, simplify it. This first step isn't even calculus, just algebra. Once you have that, good to go. Find your dy dx. Part B, this one is a quotient rule problem. So here's the first step. Now, technically, you do not need to even simplify this all the way. There's no rule in Calc BC that everything has to be simplified to a certain extent. So this would be presumably a correct answer for free response. Now, if it were a multiple choice question, it's possible that this form of the answer isn't what's showing up as the right choice. So in that case, maybe you do need to simplify to get it to match the answer choices. The square root of x in here is the same as x to the 1/2. Derivative is 1/2 x to the negative 1/2, but I'm choosing to write it in a slightly different way that made it easier to simplify once I made the decision to do that. So that's a good one to give a try. C is another quotient rule. Try it if you like. D involves quotients, but the simpler approach than quotient rule twice would be to just use trig identities. Sometimes applying a trig identity can make your life a lot easier. We're going to see that throughout the year. All right, so here's my dy dx on that one. 6.2, just practice with second derivatives. The first derivative here is a simple one. You should have it memorized. The second derivative gets a little scarier. Be really careful with product rule and then the negative sign. This line of work right here would be a correct answer. Cleaning it up further is optional. Example 6.3, we see another table example. Finding the derivative of an f times g over x evaluated at x equals 2. Again, I'm not going to worry about plugging in x equals 2 until I've got my product rule and quotient rule sorted out. This does involve product and quotient, a product within a quotient. So here's what the derivative looks like in general. Then I replace all my x's with 2, and then I use values from the table to finish that up. On the next page, we're going to review the chain rule concept. It's one thing to know the formula, but we should understand why the formula works the way it does. In the setup here, Fremd Cube team. If you're not sure what Cube is, it's a long game. It's pretty fun. Supposedly, the game was invented by Vikings, so it's appropriate for Fremd. But anyway, this team's having a pizza party. We know it's $12 per 2 pizzas, price-wise. That's like a rate of change right there. You're paying $12 per every 2 pizzas you buy. We also know the rate of feeding. 1 pizza feeds three people, so it's 1 pizza per 3 people. But if we want to know the amount of money each person needs to bring, we're kind of combining these rates with pizza being the middleman, and we are allowed to multiply. Dollars per pizza times pizza per person. You can think of it as the pizza units canceling out. So that product will give you dollars per person. That's what we're seeing here. Every time we apply chain rule, this is exactly the logic that we're doing, okay? In this example here, y equals sine x to the third. We first can find the derivative or rate of change of y with respect to sine of x. We're treating sine of x as a variable temporarily. And we multiply by the rate of change of sine with respect to x. That's why we multiply by the derivative of sine to put together chain rule here. The examples just below that are practice with chain rule, unsurprisingly. Part A actually uses chain rule twice because we have a function for x plugged into a cosecant function, which in turn is plugged into a square root function. I'm taking the derivative of the square root function treating cosecant 4x as the variable, multiply it by the derivative of cosecant 4x, treating 4x as a variable, and multiply by the derivative of the 4x. You do not necessarily need to clean this up, although a pet peeve of mine, if you have different constants multiplied together, at the very least, probably combine that into a single constant. It's quick and easy. Second one involves product rule and then two instances of chain rule. So I'm taking the derivative of the first component of the product, including the chain rule aspect, times the unmodified second component, big plus sign, and I take the first component unmodified, multiply by the derivative of the second, where again, I'm bringing in chain rule at the end. Yeah, there it is. All right, the third one is actually by far the easiest here, especially if you modify the original equation prior to doing the calculus. But yeah, there's the result and then final answer. This is a good segue into the next concept because implicit differentiation is actually just a version of chain rule. It's a version of chain rule that we use when we see y showing up mixed in with x's in some equation that we're supposed to differentiate, okay? Basically, the derivative of functions of y with respect to x, as you can see here, we take the derivative of the overall function, but we then have to multiply by the derivative of whatever y is with respect to x, which in some cases we don't know what it is. That's why we simply use the notation of dy dx to multiply on. So when we multiply dy dx onto derivatives of y terms, it's because of chain rule. All right. Overall, the strategy is just differentiate every term on both sides of these equations and you'll be good to go. Looking at the first one, we want to differentiate both sides with respect to x. The left side is easy because there's no y over there. We could just do this the straightforward way. Derivative of 2x is 2. The right side, I see a function plugged into another function. So, I have to use chain rule. Here's the negative, excuse me, sorry, here's the cosecant derivative with xy plugged in. Here's the derivative of xy. I'm taking the derivative of x, which is 1, times the unmodified y, plus unmodified x times the derivative of y, which is dy dx. Now, in some cases, I've seen throughout the years, students will get this far and be fine, but then they get stuck up on the algebra. Because here's the thing, the problem like this, you can't stop as soon as you differentiate because often we're trying to find the actual value of dy dx. So I have to use algebra to get this thing here by itself. In this case, I'll start by getting just the rightmost grouping by itself. Easy to do if I divide all this other junk to the other side. Then I subtract y for both sides. That's a separate term being subtracted onto the right. I divide everything by x. Divide, divide, divide. And there's an answer solved for dy dx. Likewise, in part B, I see y on the left side. I can go ahead and start with my typical shortcut rule, but then I have to multiply by dy dx for chain rule, since there was a y over there. The right side is more straightforward with quotient rule. I divide some stuff over to the right to get dy dx by itself. And yeah, you might have y and x in your final answer. That's okay. Part C, I've got two instances of product rule in addition to the implicit differentiation. Okay. Derivative of x squared is 2x multiplied by the y plus x squared times the derivative of y, which is dy dx. Similarly, for the next grouping, what's interesting here, the right side was a constant, its derivative goes to 0. Now I have all this stuff set equal to 0. We want to get dy dx by itself. It lives in two different terms. Collect those terms on the left. Anything that does not have a dy dx, move it over to the right side. And then I've combined a couple steps here. The remaining terms on the left that had dy dx, I factor out the dy dx, and I can easily divide to get an answer there. Bonus question, which I have seen show up in AP problems before. Where does this curve that's being described in part C have no slope? Well, no slope means derivative does not exist. This derivative that we found does not exist if the denominator is equal to 0. So we set the denominator to 0 and explore that. I can factor a bit. I end up with two solutions, either x is 0 or x is equal to -2 times whatever y is. And immediately I rule out x equals 0. And that's because if I try to plug x equals 0 back into the original equation for the curve, you cannot get it to work. So we're exclusively interested in x equaling -2y. But what exact x values would I plug in to make x equal -2y? Let's do a substitution. I'm going to literally replace these x's in the original again with -2y. Now I have an equation with one variable that I can solve. With algebra, the answer is kind of funky, but it does work out. Once I have a y value, I can plug it back in to my equation down at the left here to get a solution for x. All right, example set 6.6 has us practicing inverse trig derivatives. These rules we should have memorized. They're not the most common ones to show up, but they do show up from time to time. Each of these also seems to involve chain rule. So inverse sine derivative, we usually go with 1 over square root of 1 minus x squared, but instead of x, I have 2x. So we need to have 2x squared, and then multiply by the derivative of 2x. Clean it up if you like. Similar here for arc cotangent. We see this crazy radical in place of where typically there is an x, and then I'm multiplying by the derivative of this radical, which is double chain rule. Little typo here. Part C has a t, which doesn't quite mesh with the instructions. Let's assume that we're supposed to differentiate this one with respect to t, which is what I did here. Again, you got to know the rule for secant inverse in general. Replace your t with 1 over t in the couple places it shows up, and then also use chain rule. Simplify if you like. And then finally, one more example to look at. I'll leave it to you to check that one out. Section below that, derivatives of inverse functions. And you might be saying, well, didn't we just look at derivatives of inverse trig functions? This is not trig related. This is just any inverse function from algebra. Inverse functions, remember, are functions such that if you apply one of the functions to an x value, if you take f of x, for example, then you apply g to your result, it takes you back to the x value you started with. So, excuse me, I'm switching colors here. The mathematical way we usually write that is we say f of g of x equals the original x. This statement here holds true only for inverse functions. It holds true for all inverse functions. Okay. Now, there is a formula to help us work out derivatives of inverse functions. I don't have this memorized. I never have. Okay. The way I derive it is I just remember that I take this basic algebra rule about inverses and I differentiate both sides. Differentiating the left tells me f prime of g of x, then chain rule, we multiply by g prime of x, has to equal the derivative of the right side, which is just 1. If I then divide this part of it over to the right side, I have exactly the formula that we see directly below. That says g prime is equal to 1 over f prime of g of x, where f and g are inverses. Okay, let's see an example of how this shows up. I've got given information in this box here. We're supposed to find g prime of -4. Right here, this is another notation for inverses. I don't like this notation because people often confuse it with exponents, which is not what it means. but if you do see G equals what looks like F negative 1, that means G and F are inverses. So we want to find G prime of negative 4. I'll go to apply the formula that we just learned. G prime of negative 4 should equal 1 over F prime of G of negative 4. Then we run into an obstacle because we never actually knew the equation for G. And there are certainly tricks from algebra where you could derive G from F. You might remember a process where you switch X's and Y's and then resolve. But there's another approach we can take here. And it involves the fact that when we see right here, G of negative 4, that's asking us to plug negative 4 into the G function as if negative 4 was an X value. But if F and G are inverses, then negative 4 as an X value corresponds to the situation where negative 4 is a Y value in the F function. And that's what leads to my work over here on the left. I'm going to figure out G of negative 4 by actually just setting F equal to negative 4. And whatever X value I get here would be the Y value that I'm supposed to replace in here. So I'm working through it, solving for 0. I get a couple answers. I'm crossing out one of them just because I put a domain restriction here to limit us to one possible solution. And I learned that X equals 2 corresponds to negative 4. Okay. Basically, I'm saying F of 2 is negative 4, therefore G of negative 4 is equal to 2. And that's why I'm able to replace this portion here with a 2. So now I've got this thing down to 1 over F prime of 2. The rest of it's easy because we actually have an F function. I can easily then figure out what was F prime. I can plug a 2 into that. I can put that result back into my denominator, and there's your final answer. All right, moving right along. The next section is going to have you practicing derivatives involving exponential expressions. Okay. Here we see a variable x living in an exponent. Okay. Going back to the previous lesson, derivative of e to the x is e to the x. So similarly, derivative of this thing is itself. It's just now we have chain rule. Because I have an exponent other than just x by itself, I have to multiply by the derivative of that exponent. Same thing over here. If I start with a constant raised to anything with a variable, my derivative is that same constant, same variable multiplied by the derivative of that variable. Okay. Also, we have log 3 in there. That's because I had a base other than e. Derivative of 3 to the x is 3 to the x log 3, right? But then there's the chain rule part. There's the derivative of the exponent. All right. Example 6.9 looks kind of funky again. This is yet another example where this limit that I'm throwing at you is actually one of the limit definitions of derivative. It's the alternate form, which means x approaching 1, we see x minus 1. This top then is f of x minus f of 1. So basically, the function that this limit corresponds to is 7 root x. The limit here says find the derivative of 7 root x precisely when x is 1. And you could try to do it a long way of limits, but all right, sorry, I lost my train of thought there. I had to pause the video for a second. I think I was just saying that, yeah, this limit actually represents the derivative of 7 root x precisely when x is 1. So we're going to go with the shortcut. This is my f of x. Here's my f prime. Again, same constant, same exponent, log of your base, and then chain rule based on the new exponent. You now plug a 1 in everywhere you see an x. This is what you get. The final section involves practicing log derivatives. These are super, super common as well. Okay, the derivative of natural log of x is 1 over x. Derivative of natural log of something else is 1 over the something else times, you guessed it, chain rule. Okay. Excuse me. And if we have logs other than natural log, there's a similar shortcut. In fact, ooh, this one's really complicated. I did some manipulation first, algebraically. I'm doing actually a power rule shortcut first. Okay, but then when I go to do chain rule, I have to find the derivative of this inside part. 1 over whatever it is I'm taking the log of, but because it's not a natural log, I have to put in natural log of my actual base again in that denominator. And we're still not done because we had x to the third plugged into the log function. So there's another iteration of chain rule. This answer here would be fine, but if you wanted to clean it up, maybe you do something like this. The final question isn't actually exponential as it starts out. I don't see a natural log or any flavor of log, but I want to show you a special trick that ends up bringing logs into the mix. What's tricky about one like this is we know what to do if the base of an exponent is a variable. We know what to do when the actual exponent has the variable. We don't yet remember what to do if the variable shows up in 2 different spots. That one's a whole different type of thing. And the way we approach it is we take the original equation, we choose to take the log of both sides. If y is truly equal to 7x to the x squared, then its log is equal to the log of the right side. Now, why do I do that? Well, it's because one of the only ways we know to pull a variable or an exponent out of an exponent is using a log property. This thing right here that I'm hovering over, we could take the x squared and multiply it in front to look like it's x squared times log of 7x. Okay. In fact, before I even did that, I applied another log property, as you can see, to pull the 7 off of there first. Actually, I do need to do that first. That's my mistake. Once I do that, I can pull the x squared out in front of the log of x. So this would be the correct way to do it. Now I can take derivatives of both sides. I don't have a variable and an exponent anymore. I do now have an implicit situation for myself. So derivative of log y, I can say 1 over y, but I have to put dy dx. The next term, thankfully, is a constant. Its derivative goes to 0. The final term is product rule derivative. And then I just multiply the y over to the other side. All right, that's the end of lesson 6. Thanks for watching. Email or ask me in class if you have any questions.